The subject of the lecture today is vectors. Physics deals with quantities that have both size and direction. Those quantities are known as vector quantities. So a vector is a mathematical object with size and direction. A vector quantity is a quantity that can be represented by a vector. For example, position, velocity, and acceleration are vector quantities that we are familiar with from the previous lecture. Other vector quantities that we are going to encounter through the course are force, linear momentum, torque, angular momentum. Because of the fact that vector quantities have direction, mathematical operations and manipulations with vectors obey slightly different rules than scalar quantities or quantities that have only magnitude. So scalar quantities are quantities that do not have direction. For example, time, temperature, energy, mass. And because of the lack of direction for those scalar quantities, scalars are manipulated with ordinary algebra. So you can add two scalar quantities, subtract, multiply, divide. But because vector quantities have direction as well, simple algebra manipulations are not allowed. A different set of rules is necessary to manipulate vector quantities. So in this lecture, we are going to learn the set of rules that applies for vector quantities. Let's talk about vectors and their components. The simplest example of a vector quantity is the displacement vector. So if a particle changes position from point A to point B in space, we represent this by a vector arrow pointing from A to B. So a particle displaces from A to B, and so the direction of the displacement is given by the arrow indicated in the drawing. Now consider displacement between two other points in place, A prime and B prime. The distance between those points is the same, and therefore the displacement vector here is the same as the displacement vector from A to B. Furthermore, if you consider a third set of points, A second and B second, display the same distance from each other as in the previous two examples, then the displacement from A second to B second is a vector that is the same or identical to the other two vectors. So they are all identical displacement vectors, even though they are displacements between different sets of points in space. Now, if you look at the other drawing here, we have a displacement between points A and B in space. So the displacement vector here is indicated in purple. However, the way a particle gets between A and B can be done along all kinds of different paths. For example, one indicated in blue, like so, and another one that's in pink, like so. So the displacement vector doesn't tell us anything about the actual path that was taken between points A and B. The displacement vector only gives us the straight line distance and direction between the starting point or the initial point A and final point B. The vector sum or resultant is the result of performing vector addition. The vector sum represents the net displacement of two or more displacement vectors when, of course, we are discussing displacement. If we are discussing a different type of vector quantity, then the vector sum will be the sum of those vector quantities. And so here we have vectors A and B added together to give us the resultant vector S. Here the notation is a letter is used to label the vector quantity, and then An arrow above the letter indicates that that is a vector quantity. And so, the rule that can be used to add vectors graphically is the tail to head rule. So the tail to head rule states that when the vector sum is performed, we take the tail of the second vector in the sum, b. So let's label this as b and this as a. Therefore, this will be the resultant vector s. So we take the tail of b and place it at the head of a, and then the resultant vector starts from a and ends at the head of b. So one more time. We take the tail of b, that's the second vector in the sum, and place it at the head of a, that's the first vector in the sum, and then the resultant vector s starts from the tail of a and points towards the head of b. Now let's talk about some properties of vector addition. First, vector addition is commutative, so we can add two vectors in any order. The sum of a plus b is equal to the sum of b plus a. And so graphically, a and b are added in this triangle using the tail to head rule. The lower triangle here is the addition of b plus a, and again the tail to head rule was used. So the result of the two additions, a plus b or b plus a, is the same. Both provide or give the same resultant vector s. Vector addition is also associative, which means that if I'm adding three vectors, the order of addition is irrelevant, the final result is always the same. So for example, if I'm adding vectors a, b, and c, when I add a and b first and then I add c to that sum, I'm going to get the same result as if I add b and c first and then add a to the result. And so the drawing right here on the bottom shows us this. So here we have a and b added together, that gives us a plus b. So here is a plus b. Then to that we add vector c using the tail to head rule. That gives us the resultant vector of a plus b plus c. If we look to the left, we have here the sum of b plus c. So b plus c added by the tail to head rule. And then to b plus c, we're adding a, again using the tail to head rule. And the resultant is a plus b plus c. Now if you compare the two vectors, a plus b plus c and a plus b plus c, you would see that they are identical, they have the same direction, same magnitude, so they are identical vectors. So one more time, vector addition is associative, and the order in which the three vectors are added doesn't matter, it produces the same result. A negative sign reverses a vector direction. So for example, if we have the vector b pointing or directed like so, if it's multiplied by -1, that reverses the vector direction and keeps the magnitude of the vector the same. So when two vectors are added with the same magnitude in opposite direction, they will produce a zero resultant vector. And so we use this property to define vector subtraction. So d is the resultant vector of subtracting b from a, which is the same as adding -b to a. So here is vector a, here is vector b. Vector -b or -b is inverse to vector b. So then, using the tail to head rule and placing vectors a and -b like so, gives us the resultant vector d, which is equal to a minus b. So, no matter what type of vector quantity we are dealing with, those general rules for addition apply for all of them. However, keep in mind that only vectors of the same kind can be added. For example, you can add two distance vectors, or two force vectors, or two acceleration vectors, and so on and so forth, and that makes sense. But if you add a distance and a velocity vector, or a force and acceleration vector, that makes no sense. Think about it this way. If you add mass to volume, this is an example with scalar quantities, but it has the same idea, that makes no sense. It only makes sense to add two masses, or two volumes, or two temperatures, and so on and so forth. So you can only add quantities that are of the same type. And so that applies for scalars and for vectors. Adding vectors graphically, as the examples from the previous slides, is only good for general understanding of where the resultant vector of the addition of two vectors will point in space, or where is it going to be directed in space. However, this addition doesn't work very well to determine the actual magnitude of the resultant vector and the actual direction in space. So therefore, a different method is required for adding vectors, and that is the addition by components. And so what is the component of a vector? A component is the projection of a vector on an axis. And the process of finding components is called resolving the vector. The components of a vector can be positive or negative, and they are unchanged if the vector is shifted in any direction, but not rotated. So, if I parallel transport a vector in space, so keep the direction the same, but move it parallel to itself, the components remain the same. However, if I rotate the vector, then the components will change. In the drawing below here, in the figure, there's an example of a vector resolved in components. So we have a coordinate system, a two-dimensional coordinate system with a horizontal axis, the x-axis. The units are in meters. The vertical axis is the y-axis. Also, the units are in meters. Vector b here is the position vector of a point in this two-dimensional coordinate system. And so this vector here can be presented as the sum of two component vectors. We have an x component and a y component. As a matter of fact, using the previously discussed rules of vector addition, graphically, when you add the two components, they will give you a resultant vector, which is vector b. So how are these two components, the x and the y component of the vector, related to the vector itself? So let's first assign an angle that the vector in that two-dimensional coordinate system makes with the positive x-axis. Let's call this angle theta. So then the x component of that vector will be equal to, and that's the magnitude, will be equal to the magnitude of the vector itself times cosine of the angle theta, which is the angle that the vector makes with the positive x-axis. And then the y component is equal to the magnitude of the vector a times sine of the angle that the vector makes with the positive x-axis. The length and angle also can be found if the components are known. So imagine that instead of knowing the vector itself, you only know the components, ax and ay, and the angle. Actually, you don't know the angle, you don't know the components, ax and ay. So the magnitude of the resultant vector a is equal to the square root of ax squared plus ay squared. So the square root of the sum of squares of the two components. And then the angle that the vector makes with the positive x-axis can be calculated as Tangent of theta is equal to the ratio of the y component divided by the x component. So therefore, the components of the vector fully define the vector. So here you can see how we have two different representations. We have a vector in space and the angle that it makes with the positive x-axis. From that information we can calculate the components of the vector. So this representation is known as polar representation of the vector, or polar coordinates. And then we have the components of the vector, and from that we can calculate the vector magnitude and the orientation in space, meaning the angle that it makes with the positive x-axis. That representation is known as rectangular coordinates representation. The angles, when we calculate vector components, can be measured in degrees or radians. Typically, in problems that involve linear motion and certain rotational problems, degrees are used. However, in some situations, such as wave phenomena, radians are preferred. So it is important to remember that one full rotation around the circle has 360 degrees, or 2 times pi radians. And of course, in order to be able to resolve a vector by its components, it is also important to remember the definitions of sine, cosine, and tangent. Let's review the representation of vectors by components. So let's consider a two-dimensional vector A that makes angle theta with the positive x-axis in a two-dimensional coordinate system. So this vector can be presented as the sum of two vectors. Let's call those two vectors ax and ay. So the vectors ax and ay can be resolved by drawing the perpendicular from the head of vector A towards the coordinate axis. So ax is the vector component of A along the x-axis, and then ay is the vector component of A along the y-axis. And so by the rules of vector addition, vector A is equal to ax plus ay. And so ax and ay are known as component vectors of A. The magnitudes of ax and ay are known as the components of A, or the scalar components of A. So ax and ay are known as the scalar components of A, where ax is the magnitude of the vector component ax, and ay is the magnitude of the vector component ay. The scalar components of a vector are very important because with those we can actually do calculations. And so we are going to predominantly work with the scalar components when we deal with vector quantities. We are not going to work much with the component vectors. So then, based on the picture here, I can calculate the components of vector A by using trigonometry. So ax is simply equal to the magnitude of A times cosine of theta, and ay is simply equal to the magnitude of A times sine of theta. So I started here with knowing the magnitude of the vector A and the orientation in space given with the angle theta. From that, I was able to find the components of that vector along the x-axis and along the y-axis. And so, when a vector is presented to us as magnitude and the angle that it makes with the positive x-axis, we call this polar coordinate representation. Now imagine that we only know the scalar components, or just the components of a vector. So we know ax and we know ay. So these are the magnitudes of the vector components. Okay, so then I can find the magnitude of the resultant vector when I add vectors a, y, and ax. And so this would be this vector, and I want to find the magnitude of it. So the magnitude of A is simply the square root of ax squared plus ay squared. If I wanted to find the angle theta, then I have to find the tangent of that angle. So tangent of theta is equal to ay divided by ax, and from here theta is the inverse tangent of ay divided by ax. So when a vector is presented as a set of two components, the x component and the y component of that vector, this is known as rectangular coordinates representation. And so let's sum it up. If I know the magnitude of the vector in space and the angle that makes with the horizontal x-axis, then from here I can find the components. Ax is equal to a cosine of theta and ay is equal to a sine of theta. Or if I knew the components ax and ay, from here I can find the vector itself by magnitude, and that is ax squared plus ay squared under square root. And I can find the angle that the vector makes with the positive x-axis, and that is the inverse tangent of ay divided by ax. So those two are extremely important to know when you're dealing with vector quantities, because they help you find either the components or the resultant vector and its orientation in space, and this is important for solving problems involving vector quantities. So we discussed the addition of two vectors. We know that the resultant vector of the addition of two vectors is written as a vector equation as shown here. However, I already mentioned that actual calculations cannot be done by using or by doing vector addition of actual vectors. We must use the components of those vectors to do the addition. So I already discussed how to find the components of a vector when we know the magnitude of that vector and the angle that it makes with the positive x-axis. However, I need to find a way to present a vector in component form which still involves vectors in that representation. And so, in order to do that, I will introduce a new concept, and that is the concept of unit vectors. Let's start with a simple situation, and that is a two-dimensional situation. So we have a two-dimensional coordinate system with horizontal axis x, vertical axis y. So in this coordinate system, I can introduce vectors along each coordinate direction with magnitude of 1. So the vector along the x-axis I'm going to call I hat, and the vector along the y-axis I'm going to call j hat. And the property here is that I hat by magnitude is equal to 1, and j hat by magnitude is also equal to 1. And so I hat and j hat are unit vectors. The name follows from the fact that their magnitudes are equal to 1, so their lengths are equal to 1. We also talked about multiplying vector by a constant that only scales the vector. Either it makes it longer or shorter, or it will invert the vector. So then, if you look back at this original sum that I posted up here, that I wrote up here, I can then present each of those vectors, A and B, as the unit vector along the coordinate axis that they lie on times the magnitude of that vector. So let's have vector A along the x-axis, vector B along the y-axis. And so we also have our unit vectors here, I hat and j hat. And so I can then write A as the magnitude of A times I hat, and I can rewrite B as the magnitude of B times j hat. And so then the resultant vector R can be rewritten as A times I hat plus B times j hat. And so now this is known as the unit vector representation of a vector quantity. So unit vector representation. Here, notice that since I already know the components, I can use the information that I derived on the previous slide to find the magnitude of R and the orientation of R if I needed to. Now let's see how a vector is represented in three-dimensional coordinate system, in three-dimensional space. Here's an example of a three-dimensional coordinate system. We have an x, y, and a z-axis as the third axis. There's two ways to draw, or typically the coordinate system is drawn. This representation like this, or this representation. Both cases are identical, just the perspective from which the coordinate system is viewed is different. This is a right-handed coordinate system, meaning that if you take your right hand and you place your thumb along the x-axis, your index finger along the y-axis, then your middle finger should point along the z-axis. So in that coordinate system, the unit vectors are as follows: I hat along the x-axis, j hat along the y-axis, and k hat along the z-axis. And same here, I hat along the x-axis, j hat along the y-axis, and k hat along the z-axis. So, as I already defined them, the unit vectors have magnitude of 1, and each points along that particular coordinate direction. So then, any vector in three-dimensional space can be represented as the sum of its components multiplied by the appropriate unit vector. So let's see how that looks like. Here is my three-dimensional coordinate system, x, y, z axis. The unit vectors I hat, j hat, and k hat are also shown. And this is my three-dimensional vector R. So first I need to find the vector components of r along each coordinate direction. So for that I'm going to draw a perpendicular straight down towards the xy plane. And now from here I'm going to draw perpendiculars towards the x and the y axis. So this is Rx, this is Ry, and then the perpendicular towards the z-axis gives us Rz. And so the vector r can be written as the vector sum of Rx plus Ry plus Rz. And in unit vector form, it can be written as Rx I hat plus Ry j hat plus Rz k hat. Again, when we do calculations such as addition, subtraction, multiplication of vectors, we always go in unit vector notation and work with the components of the vector. Let's now illustrate the process of vector addition, and let's start with a two-dimensional example. So in a two-dimensional coordinate system, x and y, I have two vectors, a and b, that I want to add together. So I already conveniently placed them with a tail to head arrangement. So now, in unit vector notation, the vectors look like so. We have ax and ay. Those are the components of a. And for b, we have from here to here bx and by. And then the resultant vector let's call it r, is according to the rules this vector, and its components will be the sum of ax and bx along the x direction and ay and by along the y direction. So let's write it this way. So now let's look at the unit vector representation of the vectors and how we add them together to get that result. So A is equal to ax I hat plus ay j hat, and B is equal to bx I hat plus by j hat. So now if you look at my drawing right here, you see that essentially what is happening is the x component of r is equal to the sum of the x components of a and b. And so if you look at the unit vector representation, you can see that the x component of a is multiplied by I hat, and the x component of b is multiplied by I hat. So when I'm adding the two together, essentially I'm factoring out I hat. Similarly for the y component of r is equal to the y component of a plus the y component of b. And so when you look at the unit vector representation of those two vectors, the y component of a is multiplied by j hat, and the y component of b is multiplied by j hat. So if I'm adding the components, that's the same as adding those two terms, factoring out j hat. So then a plus b is equal to ax I hat plus ay j hat plus bx I hat plus by j hat. So this then can be written as ax plus bx I hat plus ay plus by j hat. And so ax plus bx is rx, ay plus by is ry. So rx I hat plus ry j hat. And so the x component of the resultant vector is the sum of the x components of vectors a and b. And the y component of the resultant vector is equal to the sum of y components of vectors a and b. So when you're adding vectors, all you gotta do is add the components along the same coordinate direction to get the component of the resultant vector. That is really the rule. The same process applies if the vectors are three-dimensional. So again, this is a two-dimensional case. However, it can be extended to 3 dimensions, or it can be simplified to 1 dimension. The rules still apply. You just add the components in front of the identical unit vectors, and the sum of those components will give you the component of the resultant vector along that coordinate direction. I already mentioned the rules about multiplication of a vector by a scalar quantity, but let's do it again just to reinforce the concept. So multiplying a vector z by a scalar quantity c results in a new vector. The magnitude of the new vector is the magnitude of the original vector z times c. The direction of the new vector is the same as the original vector z, or opposite if c is negative. So if c is positive, the original direction remains the same. If c is negative, the direction inverts. So to achieve the multiplication of this vector by this scalar, we multiply each component by the scalar. If we are dividing the vector by a scalar, we are multiplying by the inverse of that scalar, so 1 over c. And so here is a simple example. Multiply vector z by 5, where z is equal to negative 3i plus 5j. So then 5z would be equal to 5 times minus 3, so that's negative 15i, plus 5 times 5, 25j. Before we move on and talk about multiplication of vector quantities, let's give a few examples of polar coordinate representation, rectangular coordinate representation, and also addition of vectors by components. Let's find the components of a vector defined with 5 and 30 degrees. So magnitude of 5 and orientation 30 degrees with respect to the positive x-axis. So let's first sketch this situation in two-dimensional coordinate system. So x and y. So the vector has magnitude of 5. And the angle here, theta, is 30 degrees. So we want to find the component of the vector. So let's call this vector A. And we want to find AX and AY. Alright, so we know from the definitions that AX is equal to A cosine of theta, and AY is equal to A sine of theta. So then AX is equal to 5 cosine of 30 degrees, which is equal to 4.3, and AY is equal to 5 sine of 30, which is 2.5. And so this is an example of knowing the polar coordinate representation of a vector with its magnitude and orientation, and finding its components using the definitions. Now let's find the magnitude and the direction of a vector that was given by the coordinates 5 and 8. So this now is a rectangular coordinate representation. Let's sketch this problem and let's see what we can do about it. So here is my coordinate system. The coordinate 5 is along the x-axis, 8 is along the y-axis. So if I complete this rectangle, the vector will be along the diagonal. So I want to find the magnitude of this vector, or in other words, the length of this diagonal, and also the angle that it makes with the positive x-axis. So the definition of the magnitude of a vector when we know the components states that A will be equal to square root of ax squared plus ay squared. So that is a square root of 5 squared plus 8 squared. This is equal to 9.4. So that's the magnitude of A. Now let's find the angle. The angle theta will be equal to the inverse tangent of AY divided by AX. So that is the inverse tangent of 8 divided by 5, which gives us 58 degrees. So this is the way to find the magnitude of a vector and the direction of this vector in space by knowing the rectangular coordinates that define the position of the head of the vector in two-dimensional space. So this formalism, converting from rectangular coordinates to polar coordinates or from polar coordinates to rectangular coordinates, can be applied for any kind of vector quantity. It can be applied for displacements, for velocities, accelerations, forces, momenta, any vector quantity. The rules are the same, the math is the same. Now let's add two vectors. Let's add the vectors given by 3 and 5 and -2 and -2. Let's call the first vector A. So vector A is given by 3i hat plus 5j hat. Remember, the numbers in here are the coordinates, the x-axis coordinate and the y-axis coordinate. So therefore, I can present the vector in vector form as a unit vector representation like so. Similarly, the second vector, let's call it B, will be -2i hat minus 2j hat. So now let's add the two vectors. So A plus B is equal to 3i hat plus 5j hat plus -2i hat minus 2j hat. Let's group the terms with the same unit vector together. So this will be 3 times I hat minus 2 times I hat plus 5 times j hat minus 2 times j hat. And so now this will be equal to 3 minus 2 I hat plus 5 minus 2 j hat. Finally, that gives me 1 I hat plus 3 j hat. So the resultant vector R of the addition of A and B is 1 I hat plus 3 j hat, or in other words, that is a vector represented with components of 1 and 3. Now I can also find the magnitude of R. The magnitude of R is going to be equal to 1 squared plus 3 squared under a square root, which is equal to 3.16. And I also can find the orientation of this vector in space by calculating the inverse tangent of the y component divided by the x component. So theta is equal to the inverse tangent of 3 divided by 1. And that is equal to 71.6 degrees with respect to the positive x-axis. So from here you can see that unit vector representation is extremely convenient to be able to do vector addition and also then determine the magnitude of the resultant vector and the orientation in space without actually having to do any graphical addition or representation of the vectors. You can simply work with the numbers as basic equations, and just performing simple algebra will give you the results. This same procedure is extended for three-dimensional vector quantities. So a three-dimensional vector will have an extra component added to it that corresponds to the component along the z-axis. So it will have a term that will have k hat, the unit vector k hat. However, the addition is performed the exact same way, except for we are going to have an extra term added to the result. Now we are ready to move on to talk about multiplication of vectors. Because vector quantities are defined by magnitude and direction in space, multiplication of vectors is not as simple as multiplying two scalar quantities. As a matter of fact, there are two different kinds of vector multiplication. So let's first start with the scalar product, also known as dot product. So the dot product of two vectors is written as A dot B, and by definition is equal to the magnitude of A times the magnitude of B times the cosine of the angle between the two vectors. The result of a dot product is a scalar quantity. So we are multiplying two vector quantities, but the result is a scalar quantity. That is true when the multiplication is a dot product. So when we do a dot product multiplication, we can write each of the vectors in their unit vector representation and then multiply each term from the first vector by each term of the second vector using dot products. And the result is shown right here. The result of the dot product of two vectors is just the sum of the products of the identical components of the two vectors. Let's show how this result is achieved. In order to show the derivation of the result of a dot product, first we must talk about the dot product of unit vectors. So here we have a two-dimensional coordinate system, x and y, and the two unit vectors along each coordinate direction, the I hat and j hat. So by definition, the dot product of I hat and j hat will be equal to the magnitude of those two magnitudes of those two vectors multiplied and then multiplied by the cosine of the angle between the two. The angle between the two vectors is 90 degrees. So then I hat dot j hat will be equal to the magnitude of I hat times the magnitude of j hat times cosine of 90 degrees. But cosine of 90 degrees is equal to 1, is equal to 0. So this cosine here is equal to 0. So therefore, the whole dot product is equal to 0. Now let's look at the dot product of a unit vector by itself. So for example, let's do I hat dot I hat. So by definition, that will be the magnitude of I hat times the magnitude of I hat times cosine of the angle between I hat and I hat, that is 0 degrees. And so this is equal to 1. So therefore, I hat dot I hat is equal to 1. Similarly, I can show that j hat dot I hat is equal to 0, k hat dot I hat is equal to 0, k hat dot j hat is equal to 0, and I can flip the order in which the unit vectors are multiplied, and I'm going to get those same results. I also can show, as I did with I hat dot I hat, that j hat dot j hat is equal to 1 and k hat dot k hat is equal to 1. And so here you can see how the dot product of the same unit vector with itself is equal to 1, as I showed, and then the dot product between two different unit vectors is always equal to 0. So then I can apply this in the multiplication of two vectors. So let's consider a two-dimensional situation, because it is a little bit straightforward to draw. So let's take two vectors A and B. So we have vector A like that and vector B like that. The angle between the two is phi. So according to the definition, A dot B is simply equal to magnitude of A times magnitude of B times cosine of the angle between the two vectors. So this is a result that I can calculate as long as I know the magnitude of A, the magnitude of B, and the angle between the two. Imagine that I do not know that information, but I know the unit vector representation of those two vectors. So let's calculate the dot product A dot B using unit vector representation. So in unit vector representation, A will be equal to AX I hat plus AY j hat plus So let's keep it two-dimensional. And vector B will be BX I hat plus BY j hat. So then A dot B is simply AX I hat plus AY j hat dot BX I hat plus BY j hat. Let's group the terms that have the same unit vector in them together, and actually let's multiply each term from the first vector by each term of the second vector in a dot product. So then this becomes AX I hat dot BX I hat plus AX I hat dot BY I hat plus AY j hat dot BX I hat plus AY j hat dot BY j hat. Now, for each of those products, we have a scalar AX or BX, for example, in this first term, multiplied by a unit vector. And then in the second term, we have two more scalars, each multiplied by a unit vector. In the third term, the same thing, two scalars multiplied by unit vectors. And the same in the fourth term. So that means that I can factor out the scalars, and then we'll end up with only multiplying the unit vectors in a dot product. And that makes sense as well, because the dot product only is valid for vector quantities. So let's rewrite the entire sum as the product of the two components, and then the two unit vectors in each term in a dot product. So here's what we get. axbx times I hat dot I hat, axby times I hat dot j hat, aybx times j hat dot I hat, and plus ayby times j hat dot j hat. From the previous slide, we know that the dot product of the same unit vector with itself is equal to 1. So here we have 1, and here we have 1. And then the dot product of two different unit vectors is equal to 0. So this is a 0 and this is a 0. So then I get my final result, a dot b is equal to ax bx plus ay by. So this is the sum of products of the identical components of the two vectors. And so this can be generalized for any three-dimensional set of two vectors multiplied in a dot product. So this here is two-dimensional. In three-dimensional situations, the dot product is simply the x component multiplied together plus the y components multiplied together plus the z components multiplied together. So this is 3D. And so as you can see, these are just the sum of three numbers. The result is a number or a scalar. So again, by definition, the dot product of two vectors is a scalar quantity. Because it's a scalar quantity, the order in which the two vectors are taken in the dot product is irrelevant because the final result will still be the same. Now let's talk about the other type of vector multiplication. So two vectors can be also multiplied in what is known as a vector or cross product. The cross product of two vectors with magnitudes a and b separated by angle phi produces a vector with magnitude c equal to the product of magnitudes of a and b and the sine of the angle phi between them. So the cross product of two vectors is a vector quantity with magnitude calculated with this formula. And this is very important. Unlike for the dot product where the result was a scalar quantity, the result of a cross product is a vector quantity. This vector quantity has magnitude calculated with this formula. We are also going to talk about the calculation of this vector quantity as a vector, not the magnitude of it, but the components of it. Another important property of the result of a cross product is that the resultant vector is in a direction that is perpendicular to both original vectors. So the resultant vector of a cross product is perpendicular to both the original vectors. The direction of the cross product result, the resultant vector, is determined by the right-hand rule. So place vectors tail to tail, sweep fingers from the first to the second, and the thumb points in the direction of the resultant vector. And this has to be done with your right hand, therefore right hand rule. So one more time, in your right hand, first place the vectors tail to tail, and then use the fingers of your right hand from the first to the second vector. So sweep in that direction. And then the thumb of your right hand will point in the direction of the resultant vector. If vectors A and B are parallel or anti-parallel, A cross B is equal to 0. That is because the angle between the two is either 0 degrees or 180 degrees, and sine of 0 or 180 is equal to 0. The magnitude of the cross product A cross B, which also can be written as such, that's the absolute value of A cross B, So the magnitude has a maximum when A and B are perpendicular to each other. And it's a minimum when the two vectors are parallel or anti-parallel. Here is an illustration of the right-hand rule for cross product of two vectors. So the example here is for the cross product A cross B. Now, since this result is a vector quantity, it's very important to keep track of the order in which the two vectors are presented. So vector A is the first vector in the cross product, B is the second vector. So when using the right-hand rule, you would place the fingers of your right hand in the direction of the first vector in the cross product, so A, and you're going to sweep your fingers towards the direction of B until then they line up with B. The thumb of your right hand points in the direction of the resultant vector C. The second example, the second row, shows you the cross product B cross A. So now B is the first vector in the cross product, so you will line up the fingers of your right hand along the direction of B. Then you're going to sweep towards A until your fingers line up with A. The thumb of your right hand points in the direction of the resultant vector C, right here. As you can see from those two examples, the order in which the two vectors are taken in the cross product matters. When A is first and B is second, the result of the cross product points up. When B is first and A is second, the result points down. So that means that if you change the order of the vectors in the cross product, you are going to reverse the result of the cross product. And so B cross A is equal to minus A cross B. Now let's discuss the cross multiplication of two vectors when done by components in unit vector representation. First, I will discuss the cross product of unit vectors, because that is important to achieve the final result of the cross product of any two vectors. So here is my two-dimensional coordinate system with two unit vectors I hat and j hat. Let's do the cross product of I hat with itself. I hat cross I hat, this is equal to the magnitude of I hat times the magnitude of I hat times the sine of the angle between the two vectors. That angle is 0 degrees. So then this is equal to I hat magnitude times the magnitude of I hat times sine of 0 degrees. That is equal to 0. The same can be shown for j hat cross j hat and k hat cross k hat if I have a three-dimensional situation. Now let's do the cross product between I hat and j hat. So I hat cross j hat will be equal to the magnitude of I hat times the magnitude of j hat times sine of the angle between the two. The angle between those two vectors is 90 degrees. So that is I hat times I hat sine of 90 degrees, which is equal to 1. So the cross product of I hat and j hat is equal to 1. Now, from the property of cross product, if I swapped the places of I hat and j hat, that should give me minus 1. So let's write it down. So j hat cross I hat should be equal to minus 1. And so here it is. I have a rule that the unit vectors obey when they are multiplied in a cross product. So I hat cross I hat is equal to 0. J hat cross j hat is equal to 0. K hat cross k hat is equal to 0. And then we have I hat cross j hat is equal to 1. Then we have j hat cross I hat is equal to minus 1. Then I can also show that j hat cross k hat is equal to 1, and k hat cross j hat is equal to minus 1. And finally, k hat cross I hat is equal to j hat, and I hat cross k hat is equal to minus j hat. And so this is the set of rules that the unit vectors obey when multiplied in a cross product. If you have asked yourself, why is the result of these cross products just a number when the resultant vector is, when the result of the cross product is a vector quantity, then you would be correct to ask those questions. So the first set of examples that I gave here refer to the magnitude of the cross product. So the magnitude of I cross, and I hat cross j hat is equal to 0 or 1. And then the magnitude of I hat cross j hat should be equal to also 1. Now the second set of rules shown needs to be also modified. The first row produces the correct result because the result of these cross products are 0, but the rest are not equal to what I already wrote. Why is that? Well, according to the right-hand rule, if you look at this example, you would place your fingertips of the right hand along the vector I hat, then you're going to sweep towards j hat, and then the thumb of your right hand will point in the direction of the resultant vector. That vector will lie along the z-axis. And so, since we are dealing with unit vectors, the result will be a unit vector, and that will be k hat right here. So then, that means that I hat cross j hat is not equal to 1, because it's not a number, it's not a scalar, the result is a vector quantity, but it's going to be equal to k hat. Then if I flip the positions of I hat and j hat, the result will be equal to minus k hat. Similarly, when I do the product of j hat and k hat, the fingers of my right hand point along the j hat direction, then I sweep towards the k hat direction, the thumb of my right hand points in I hat direction. So j hat k hat is equal to I hat. And then when I flip the positions of k hat and j hat, k hat cross j hat is equal to minus I hat. And finally, k hat cross I hat is equal to j hat as shown, and I hat cross k hat is equal to minus j hat as shown. So again, the cross product of two vectors is equal to a vector that is perpendicular to both of the original vectors. The magnitude of the cross product is calculated using that definition. Now let's multiply vectors A, shown in unit vector notation like this, and B, shown in unit vector notation like this, in a cross product. So in unit vector notation, this is vector A, this is vector B. What I'm going to do is I'm going to multiply each term of A by each term of B with a cross product. So what I get here is the sum of 9 terms. And now I'm going to group or rearrange the terms here in each cross product by bringing out the components in front of the cross product, and then only leaving the cross product between the unit vectors in each of those terms. Now I'm ready to look at the individual cross products between the unit vectors. So we know that I hat cross I hat is a 0. And then j hat cross j hat will be a 0, and k hat cross k hat will be a 0. For the rest, I'm going to apply the rules that I derived on the previous page, right here. So I hat cross j hat will be equal to k hat. I hat cross k hat will be equal to minus j hat. Next is j hat cross I hat. This will be equal to minus k hat. Next is j hat cross k hat. This is I hat. Next is k hat cross I hat. This will be equal to j hat. And then last we have k hat cross j hat. It should be minus I hat. So now I have 6 terms left, and 2 terms have k hat vector, 2 terms have j hat vector, and 2 terms have the I hat vector. So I'm going to group the terms together. So the final result of the cross product is a vector that has x component that's calculated as this sum of 2 terms, a y component that's calculated as the sum of those 2 terms, and a z component that is calculated as the sum of those 2 terms. Now there is a different way of performing the cross product known as determinant method. So the determinant method for cross product is somewhat more systematic in a way to determine the result, and it takes less dealing with indices and might be less prone to mistakes. So let's talk about it. So again, I start with my 2 vectors A and B written in unit vector notation, and then using the unit vectors and the components of each vector, I'm going to write a 3x3 determinant that looks like so. On the first row of the determinant, I place the unit vectors in order: I hat, j hat, k hat. The second row has the components of vector A, so ax, ay, and az. The third row has the components of B, bx, by, and bz. So now I can decompose this into the sum of 3 two-dimensional determinants. Here is how this is done. The first term in the sum will correspond to the following determinant. It's a 2x2 determinant with components ay, az on the first row and by, bz on the second row, and then this is multiplied by I hat. So how did I achieve this? Well, think about it this way. If I cross the first row and column like this, what's left is this block here, which corresponds to what I put in this 2x2 determinant. And then I'm multiplying the 2x2 determinant by the element that was crossed. So that is I hat. So then I can perform the same operation with j hat and k hat and add 2 more terms to this sum. So by that rule, if I crossed j, what I'm left with would be ax, az, bx, bz in a 2x2 determinant multiplied by j hat. So let's put it down. It is extremely important to remember that this second term comes with a minus sign. The last term comes in with a plus sign, and I'm going to achieve that by crossing k hat in the first row. So what's left is this block here, which has elements ax, ay, and bx, by. So that's going to be my 2 by 2 determinant multiplied by k hat. That will be my third term. Now I can calculate those determinants. So when we're calculating 2 by 2 determinants, first we multiply the terms on the diagonal that starts from top left to bottom right corners. And from the product of those two, we subtract the product of the terms that start at the top right towards bottom left. And so the first determinant is AYBZ, so AY times BZ minus AZ times BY. Similarly, the second one will be AXBZ minus AZBX. And this is multiplied by J hat. And then for the last determinant, we'll have AXBY minus AYBX multiplied by K hat. And now if you compare this result to the result shown above from the lengthy cross-product multiplication, you'll find out that they are the same. So the determinant method is definitely shorter and maybe easier to perform with less possibilities of errors if you follow the defined steps as shown here. So let's summarize. The cross product of two vectors A and B with an angle phi between them is a scalar quantity. So the dot product A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. This is a result that can be calculated when you know the magnitude of A and B and the angle between the vectors. However, if you do not know those quantities, but you know the vectors in unit vector presentation, then you can do the dot product, and the result will be the sum of the products of the quantities along the same directions, of the components along the same directions for each vector. So AX, BX, AY, BY, AZ, BZ. Related to that is also the dot product of unit vectors. So the dot product of a unit vector by itself is always equal to 1, and the dot product of a unit vector by another unit vector is always equal to 0. Finally, reversing the order of the two vectors in the dot product does not change the result. And of course, the title of this slide should be dot product, not cross product. So all of these apply for dot products. Now let's summarize the cross product of two vectors. So consider vectors A and B with angle phi between them. The cross product is a vector C. So it's a vector quantity with a magnitude that is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. If I wanted to calculate to find the components of vector C as a vector quantity, then I must perform the cross product operation using the vectors A and B in unit vector notation. So the cross product of A and B is the vector C, which we can calculate in unit vector notation by substituting A and B in their unit vector representations and going through the cross product the way I showed in the previous slides. The result is this vector. The x component of C is the term before I hat, so that is AY BZ minus AZ BY. The y component of C is the term before J hat, so that's minus AX BZ plus AZ BX. And the z component of C is the term before K hat, so that is AX BY minus AY BX. So basically, if you know the components of A, so if you know AX, AY, and AZ, and also BX, BY, and BZ, following this result here, you can just plug them in and find out what the resultant vector C is in component form. And I also discussed the determinant method of calculating the cross product, so let's summarize that one as well. Starting with the two vectors A and B in unit vector notation, the determinant that I need to form is a 3 by 3 determinant, with the first row being formed by the unit vectors I hat, j hat, k hat. The second row is the components of vector A, so ax, ay, and az. The third row is the components of vector B, bx, by, and bz. So if I cross the first element on the first row, so that is I hat, like so, what's left is this block here. So that is my 2 by 2 determinant, which I'm going to multiply by I hat. Then for the second term, I have a minus sign. And then in my determinant, if I scratch or cross out j hat, what's left is ax, az, bx, bz. So this is my 2 by 2 determinant multiplied by j hat. And finally, I'm going to cross out k hat, like so. What's left is this block here that contains ax, ay, bx, by. So that's my third 2 by 2 determinant that I'm multiplying by k hat. And so by the rules of multiplication of, or how we calculate 2 by 2 determinants, I start with upper left corner multiplied by the term in the lower right corner. And then from that I subtract the product of the term in the upper right corner and the term in the lower left corner. So AYBZ minus AZBY. And this is the x component of the resultant vector. From the second determinant, I get the y component of the resultant vector. And from the third determinant, I get the z component of the resultant vector. So this here is Cx, this is Cy, and this is Cz. Once I know those components, how do I find the magnitude of C? The magnitude of C is just the square root of Cx squared plus Cy squared plus Cz squared. The angle that it makes with the positive x-axis, theta, is calculated as the inverse tangent of Cy divided by Cx. And the angle that it's making with the z-axis, phi, is equal to the inverse cosine of Cz to C. And finally, the rules for cross products of unit vectors. The cross product of a unit vector by itself is a 0. And then the cross product of I hat and j hat is k hat. The cross product of j hat and I hat is minus k hat. The cross product of j hat and k hat is I hat. The cross product of k hat and j hat is minus I hat. The cross product of k hat and I hat is equal to j hat. And the cross product of I hat and k hat is equal to minus j hat. So these cross products you guys are expected to know and be able to derive by yourself using the simple definition of cross product and the right-hand rule. So when you come to tests, you're not allowed to have these written on your formula sheets. You need to know how to derive them. This concludes the lecture on vectors.